In this video, we're going to do some extra examples looking for extrema values. So we're going to find and classify all of the relative extrema. So we want to find where the extrema are and determine whether they're local maximums or local minimums. So let's start with our first example here. So f of x is 2x to the 6 minus 2x to the 5. So first of all, let's think of the domain. So this is a polynomial. So we know the domain is all real numbers. Okay, so all x values are in the domain. So we want to find our critical numbers. So we take the derivative, which is going to be 12x to the 5 minus 10x to the 4, which we could factor. So I can pull out 2, and then, 2x to the 4. And then I'm going to be left with 6x minus 5. Okay, so then we want to know, well, where is our first derivative equal to 0? Because that's where we're going to get critical numbers. So that's 2x to the 4 times 6x minus 5 should equal 0. So that means that either this 2x to the 4 is 0 or 6x minus 5 is 0. So we get 2x to the 4 equals 0, or 6x minus 5 is 0. The first one gives us that's 0 when x is 0. And for the second one, this is going to be 0 when x is 5 over 6. Which, let's just approximate that. So this is approximately 0.833, just so we know. Okay, so those are two critical numbers. Okay, so we might have extrema values there. And then we want to see, okay, where is the first derivative not exist? Okay, here it's a polynomial, which means that it always exists. Okay, so we don't have to worry about those ones. So in order to classify them, I'm going to use the first derivative test. So I'm going to put these on a number line. Okay, so it splits at 0, and then it splits again at 5 over 6. Probably I wanted that to be a bit further down. Okay, so that's where the derivative is 0. So I want to check somewhere in between. So let's say I check -1. So I'm plugging into the derivative. So I'm going to have 2 times -1 to the 4, and then -6 minus 5. So 2 is positive, -1 to the power 4 is going to be positive, and -6 minus 5 is negative. So I have 2 positive times a negative. This is going to give me a negative, which means that I am decreasing in this interval. Something between 0 and 5 over 6, it may be 1/2. Okay, so if I plug that in, it's 2 times 1/2 to the power 4 times, now 6 times 1/2 is 3 minus 5. So again, I have a positive, and a negative. So this interval is going to have a negative derivative, which means that it's still decreasing. Something bigger than 5 over 6, I could pick 1. So that's going to be 2 times 1 to the power 4 times 6 minus 5. So it's a positive, and a positive. So here I'm going to be a positive, which means that I am increasing in that interval. Okay, so now if I look at my critical numbers, okay, which are these two values here, so this is where I could have my max or min. We see that at x equals 0, we have neither a max nor a min because I decrease and then I decrease some more. So the graph is just leveling out and then keeps decreasing. Okay, so it's not a max or min. But at x equals 5 over 6, I decrease and then I increase, so it looks like we're getting a minimum. Okay, so here I'm going to have a relative minimum value. So I want to find the y value. So when x is 5 over 6, we get y is f of 5 over 6, so we're using the original function. So this is 2 times 5 over 6 to the 6 minus 2 times 5 over 6 to the 5. And if I compute that, what are we going to get? So we get something that's approximately negative 0.134. Approximately, if you plug that in. So that means that f of x has a relative minimum of y approximately equal to negative 0.134 at x equals 5 over 6. Okay, so kind of like to know what that number is. Okay, so let's try another one. So g of x is negative 2x plus 1 to the power 2/3. So because this is a cube root, so the cube is on the bottom of this exponent, that means I can plug in any x value. It doesn't matter if this thing inside is positive or negative. So again, we're going to have the domain being all real numbers. Okay, so now we're going to try and find the derivative. So the negative can come out. We're going to bring the 2/3 down, and it's going to be 2x plus 1 to the power 1 less, so that's going to be to the negative 1/3. And then times the derivative of the inside, which is 2. So we're going to get negative 4 over 3 times the cube root of 2x plus 1. So, where does g prime of x equal 0? Well, when we've written it like a fraction like this, it's actually going to be 0 when the top is 0. Okay, so that means when negative 4 equals 0, but that doesn't make any sense. So that means that there's no solutions. Okay, so there's no x values where the derivative is 0. Okay, so now what about where the derivative doesn't exist? Okay, so that's going to be when the bottom is 0. So that's going to be when the cube root of 2x plus 1 is 0, which is the same as saying that 2x plus 1 is 0. So if we solve for x, we get x is negative 1/2. Okay, so this is going to be our only critical number. Okay, so then we can do our number line. And we just need to have negative 1/2 on it. So that's where the derivative doesn't exist. So I can check, say, maybe negative 1. So if I plug into the derivative, this is negative 4 over 3 cube root of negative 2 plus 1. So that's the cube root of negative 1, which is negative 1. So I get a negative over a negative. This is actually going to be a positive. So I'm going to have that the function is increasing on that interval. If I plug in something bigger than negative 1/2, maybe 0, then I'm going to have negative 4 over 3 cube root of 0 plus 1. So that's cube root of 1, which is 1. So this is going to be negative 4/3. Okay, but you could think it's a negative over a positive. That means it's going to be a negative. So now I'm decreasing. So I increase up until this point, and then I decrease down from it So this is going to be a relative maximum here. Okay, now we want to be careful. Remember that the domain was all real numbers, so -1/2 is in fact in the domain. So in our graph, it's likely going to be a sharp turn because it exists there, but the derivative does not. Okay, so we should probably find the y value. So when x is -1/2, y is going to be g of -1/2, which is going to be -2 times -1/2 plus 1 to the power 2/3. So this is -0 to the 2/3, which is 0. Okay, so what that means is that g of x has a relative or local maximum of y equals 0, which occurs at x equals -1/2. Okay, so that's our only relative extrema for this graph, or for this function. So let's try another one. So here again, we want to find and classify all the relative extrema. So what does my domain look like? So let's just note e to the 2x, so e to anything actually, is always strictly bigger than 0. Okay, so that means the denominator can never be 0. And it's in fact never negative, but in particular it's not 0. So our domain, again, is going to be all real numbers. Okay, so now we don't have any asymptotes or anything like that. So let's find the derivative. We're going to have to use the quotient rule. So it's going to be the derivative of the top. So that's 4x cubed times the bottom, e to the 2x, minus the derivative of the bottom, which is e to the 2x times 2, times the top, which is x to the 4, all over the bottom squared. Okay, now I can factor this. I see that I can pull out 2x cubed and e to the 2x. So what's left over from the first term is just 2, and what's left over from the second term is just x. And this is over e to the 2x all squared, or e to the 4x. I left it like this because I can now cancel one of these e to the 2x's with one of the ones on the bottom. And I get that my derivative is 2x cubed times 2 minus x over e to the 2x. Okay, so that's my derivative I'm going to be using. Okay, so now we want to know where's the critical numbers. So where's my derivative equal to 0? So that's when the numerator is 0. Okay, which is going to be when 2x cubed equals 0, or when 2 minus x is equal to 0. So I get critical numbers of 0 and 2. Okay, so here are some critical numbers. Oh, that didn't work at all. Still didn't work. Okay, no box there. I guess I can, oops. I can do one without a nice straight line, but. Okay, so those are critical numbers. Now we want to also see where does the derivative not exist. Okay, so that's going to be when the bottom is 0. So e to the 2x equals 0. Now we already said that e to the 2x was strictly greater than 0. Okay, now if you don't believe that, and let's say you try to take the ln of both sides, you could say ln of e to the 2x is equal to ln of 0. So that's the same thing as saying 2x is equal to ln of 0. but ln of 0 does not exist. Okay, so that's another way to see that there's no solutions here. Okay, so here we have no critical numbers. Okay, so these are our only critical numbers. So we want to see if they are local maxes or local mins. So we make our number line. Okay, so we have 0 and 2. We want to check points in between. I guess I want to see my derivative here, maybe. So let's say I do -1. Okay, so if I plug into the derivative, I'm going to have 2 times -1 cubed, 2 minus -1 over e to the -2. Okay, now, so the 2 is positive. -1 cubed is negative. 2 minus -1 is actually 2 plus 1, so that's positive. And e to any power is always positive. So what we get is a negative over a positive, which is going to be a negative. So we're going to be decreasing on this interval. Okay, if I try it with 1, I'm going to have 2 times 1 cubed times 2 minus 1 over e to the 2. So again, here I have a positive, the positive 2. 1 cubed is positive. 2 minus 1 is also positive, and e squared is also positive. So here I have a positive number, so I'm going to be increasing. If I pick something bigger than 2, let's say 3, I'm going to have 2 times 3 cubed, 2 minus 3 over e to the 6. Okay, so again, this is positive for the 2, positive for the 3 cubed, negative for 2 minus 3, and positive for e to the 6. So here I'm going to have a negative on top, a positive on the bottom, so I'm going to get a negative overall, and I'm going to be decreasing. So here at 0, it looks like we're going to have a relative min, and at 2, it looks like we're going to have a relative maximum. Okay, so we should find our critical points. So we need the y values. Okay, so when x is 0, my y value is f of 0, which is going to be 0 to the 4 over e to the 0, which is 0 over 1. Okay, so 0. And when x is 2, my y is f of 2, so that's 2 to the 4 over e to the 4, which is 16 over e to the 4, okay, which is approximately 0.293. Okay, so we could actually, if you want, write our critical points, okay, are going to be 0, 0, and 2 and 16 over e to the 4. Okay. But for our conclusion, we're going to say that there is a relative or local minimum of y equals 0, okay, at x equals 0, and a relative maximum of y equals 16 over e to the 4, which occurs at x equals 2. Okay, one more example to get through. So, what is the domain for this one? Well, here we actually have an issue. So we can't have the bottom being 0. So our domain, we can't have x being 3. Okay, so in interval notation, it goes negative infinity to 3, and then 3 to infinity. Okay, so x equals 3 is not in the domain. Now I want to find my critical numbers. So I take g prime of x, so the derivative of the top is 2 times the bottom minus the derivative of the bottom, which is 2 times x minus 3 to the 1, times the derivative of the inside, which is 1, okay, times the top, which is 2x, all over the bottom squared. Okay, now I see that I have some common factors, so I can take out the x minus 3 here to the smaller power. And I can also take out a 2, which will help a little bit. So I'm going to pull out 2x minus 3. So what I have left from the first term is another x minus 3. And from the second term, I just have a 2x. And on the bottom here, this is going to be x minus 3 to the power 4. So now I can cancel out one of these x minus 3s, so I just have 3 left on the bottom. And I can simplify inside these brackets, so I get 2 times, it's going to be negative x minus 3 over x minus 3 to the 3. Okay, which I could pull out a negative so it looks a bit nicer. So negative 2x plus 3 over x minus 3 cubed. Okay, so that's my derivative. Okay, so now I want to know where is the derivative equal to 0. So that's when the top is 0. Okay, the negative 2 is never 0, so this means that x plus 3 has to be 0, which means that x is negative 3. This is in the domain. Okay, so this is a critical number. Okay, now I want to know where does the derivative not exist. Okay, that's when the bottom is 0. Okay, which is actually when x minus 3 is 0 or x equals 3. Okay, now this one is not a critical number, since not in the domain. Okay, but when we put it on our number line, we still want to put it on the number line, because remember, it's a place where the derivative doesn't exist. So it can, the increasing, decreasing, this can change there. So this x equals negative 3 is actually our only critical number. So we make our number line. So I'm going to have negative 3 on here, and I'm also going to have positive 3. Now I'm just going to make a note here. G prime of negative 3 equals 0. And over here, g prime of 3 does not exist, which also g of 3 does not exist. Okay, so this is maybe going to help me remember that this one is not a critical number. Okay, so I test something less than negative 3, so let's say negative 4. I want to still see my derivative here. So I'm plugging into the derivative. So I have negative 2 times x plus 3, so negative 4 plus 3, over negative 4 minus 3 cubed. So I get a negative, the negative 2. Negative 4 plus 3 is still a negative. And here, down at the bottom, I have negative 7 cubed, which is also going to be a negative because I'm cubing it. So I end up with a positive over a negative, so I'm going to have negative. So I'm going to be decreasing on this interval. Okay, let's pick something between negative 3 and 3, so let's say 0. So I have negative 2 times 0 plus 3 over 0 minus 3 cubed. So this is a negative times a positive over a negative, because negative 3 cubed is negative 27. So I have a negative over a negative, which actually gives me a positive. So I'm going to be increasing on this interval. If If I pick something bigger than 3, let's say 4, now I have negative 2 times 4 plus 3 over 4 minus 3 cubed. So this is a negative times a positive, because 4 plus 3 is 7. And 4 minus 3 is 1, and I cube 1, I get a positive number. So here I have a negative over a positive, which is going to give me a negative overall. So I'm going to be decreasing. So it looks like at negative 3, we're going to have a relative minimum, and maybe at x equals 3, we get a maximum value. Now you might be seeing a problem with that. So we want to remember that x equals 3 is not in the domain. Okay, which means that it cannot be a relative max or min. So there's no extrema there because there's no point there. Okay, so we actually can't have anything there, but over here at negative 3, we do have a relative minimum. Okay, because negative 3 is in the domain. So we want to find the y value. So at x equals negative 3, the y value is g of negative 3, and our function was 2x over x minus 3 cubed. So it's going to be 2 times minus 3 over minus 3 squared, right? Squared. So this is negative 6 over negative 6 squared is 36. So it's going to be negative 1 over 6. So g of x has a relative minimum of y equals negative 1 over 6 at x equals negative 3. And that's the only extrema value for this function. Damn it. Try one more time here. Kind of. I'll move this down. So that's how you can classify extrema. Now, it's good practice. I didn't use this method because technically this section comes before, but you could also classify all these extrema, well, most of these extrema values, the one where the derivative is 0, using the second derivative test. Okay, so sometimes that one is useful as well. So it might be good practice to see what that would look like. You should get the exact same conclusions though.